Okay, today we will start deriving a theoretical result about TFA. So this is an important topic, at least theoretically. In particular, what I would like to eventually prove is that we assume that R is a regular language. And we assume that M and N are two deterministic finite automata with the same language. R. Also, when I am talking about Myhill-Nerode relations or theorems, I will assume that neither of these contain any inaccessible or unreachable states. Then, if you recall, I can define a machine with respect to some equivalence relation such that we can collapse equivalent states. And I can do the similar construction on the second machine N. Okay. Eventually we will show that these two are essentially the same machine. I will define what I mean by essentially the same machine. Okay. Technically, they are isomorphic. So, as I mentioned near the end of last lecture, so these smallest machines are in some sense a property of the language R itself, instead of machines, individual machines. So, we need a way to jump from machines to languages and also from languages to machines. Of course, here languages are only regular languages and machines are deterministic finite automata, and I will assume that there are no inaccessible states. Okay, in order to understand what we are going to do, let me start with an example. Let us consider the set of all binary strings such that the last two positions contain at least one 1. Okay. Now, we make some assumption. So, epsilon does not have any last position, or maybe I just the null string. This is not assumed to be in R, whereas I assume, okay, 0 is also not in R. whereas I will assume that 1 is in R. Of course, this string of length 1 does not contain 2 last positions, but since 1 last position contains a 1, so we will assume that it satisfies the property for belonging to R. So I start with a machine, a DFA, with no inaccessible states, with quite a few states, in order to realize this regular language R. Okay. Epsilon is a string not in the language. So this corresponds to epsilon. Nothing is read so far. And it must be a non-final state. Okay. Now if I read 0, I am in this case 0. This is not in R, so I will take this as non-final. But 1 is in R, therefore if I read 1 as the first symbol, I should go to a final state. Let me designate these states as epsilon, 0, 1. The remaining 4 states are based upon the idea of remembering the last 2 symbols read from the input. So 0, 0 means the last 2 symbols read are both 0. 1, 0 means the last symbol read is 0, the last but 1 symbol is 1. Likewise, last symbol 1, last but 1 symbol is 0. And here both the last 2 symbols are 1. Okay. And from this state 0, if I read 0, I will go to 0, 0 because this is 0, 0. If I read 1, I will go to 0, 1, this state. If I read 1, then 0, I will reach 1, 0. 1 and 1, I will reach this 1, 1. And here, this is very similar to the last second position being 1. This, for example, if 0 keeps on coming here, it will continue to stay in the state 0, 0. If 1 comes here, so this will go to state 0, 1. And you can verify that these transitions are correctly depicted in this picture, unless there is a mistake of mine. Okay. Now, the reason why I introduce this language is that, machine and this language is that, let us look at a string X in sigma star. And let us look at the working of this machine. It must start in the start state. And after completely reading X, this is a DFA with no inaccessible state. So this is a unique state of the machine. Okay. Now, since this is a DFA, deterministic finite automaton, after reading X, starting from state S, the machine cannot end up in two different, I would say, states. So it's a unique state. Okay. Moreover, since there are no inaccessible states, every state, whether it is an accept state or a reject state, or a non-accept state, final or non-final state, at least some string X in sigma star will let the machine end up in that state. Okay. Now, if I look at what are the, I would say, sets of strings that lets the machine end up in this state. Maybe let me write it this way. L sigma. Okay. This is a set of all strings that lets the machine end up in this. And you can see it's only epsilon. So in a sense, this L epsilon is the language of this state. Okay. Now if I look at L0, what is the language of 0? You see that this is only 0. If I look at 1, maybe I write it. Okay, whatever. L1. The machine ends up in this state 1 if and only if the input is 1. Okay. Other than this, there are 4 other states, L0, 0, 0, 1, 1, 0 and 1, 1. So it is easy to see that L00 is nothing but the language of the regular expression. All strings that end with 0, 0. L01 is the language of the regular expression, set of all strings ending with 0, 1. Likewise, I have L10, the language of all strings ending with 1, 0, and L11, L, language of all strings ending in 1. Okay. So each state in the machine is associated with a subset of sigma star. Okay. So each state Q in Q is associated with some subset LQ of sigma star. Okay, so this is true for each. And since there are no inaccessible states, I can assume that this is non-empty. Okay. And if I start with any arbitrary x, I will end up at some state. Okay. So this means the sets, the subsets, okay, two things. First, union of all LQ, Q in Q, must be sigma star, because if I start with any element of sigma star, I will end up somewhere. And the second important thing is that if two states P and Q are different, then their intersection is empty. Okay. To sum up, I can say that these subsets LQ, Q belonging to Q, okay, partition sigma star. So the conclusion is that the subsets LQ, Q in Q star, Q, partition sigma star. How many parts are there in this partition? One corresponding to each state. That is 1 epsilon, this corresponds to L epsilon, 0 corresponds to L0, L1 corresponds to L1. So 1, 2, 3, 4, 5, 6, 7. Okay. Another important thing about this is that take any two strings, x and y. If they are in the same part, then they are both either accepted or both rejected. Okay. So now in this example, there are 7 parts in the partition. 1 corresponding to each state of the machine. Okay. Now, if I want to make this machine smaller without affecting its, I would say, language. I have no inaccessible states for that matter. But the way of doing it is by using collapsing equivalent states. Okay. So if I now look at what are the equivalent states here, see that this and this are equivalent. Why? Upon reading 0, I have a transition here. Upon reading 0, I have a transition to the same state. Okay. Upon reading 1, I have a transition to this state. Upon reading 1, I have a transition to this state. So this is also the same state. So without any problem, I can merge these two states. Okay. Likewise, you can see that maybe I use this here. If I read 0, I end up here. Here also, if I read 0, I end up here. If I read 1, I end up here. If I read 1 from this state, I end up here. So this state and this state, they are also equivalent. So I can merge them. Okay. And let us see what happens to the... So I have merged this 0 with 0, 0, 1 with 0, 1. Okay. Now let us see what happens to that partition. L epsilon continues to be epsilon. L 0, 0 now has become, it accepts 0 and all strings of length greater than or equal to 2 which end with 0, 0. Okay. And L01 is now 1 and L ending with 0, 1. And sorry, maybe I use not this calligraphic L. L10, 1, 0, it remains the same as before. One, 0. And finally L11 is the language of the regular expression 0 plus 1 star 1. Okay. Once again, this is a valid DFA accepting the same language. Okay, this language. However, and also you see this L epsilon, L00, L01, L10, L11. This is once again another partition of sigma star. Okay. So a new partition of sigma star. Now, however, I have only 5 parts. Earlier I had 7 parts, now I have 5 parts. So we say this is coarser than the previous partition. Because this has only 5 parts, the earlier partition has 7 parts. Now once again you see that there are other possibilities of merging or collapsing equivalent states. So for example, if I look at this, maybe again I take some color. Okay, no. What is the problem? Yeah. Okay. So you see that from epsilon, if I read 0, I end up here. If I read 0, I end up here. From epsilon, if I read 1, I end up here. And if I read 1, I end up here. So that means I can again merge or collapse these two states. They are also equivalent. And if I do that, I get this machine. Okay. Now if I look at the corresponding partition of sigma star created or induced by this machine, it's something like this. Zero, zero contains epsilon, 0, and language of the regular expression 0, 1. Sorry, 0, 0, ending with all strings, ending with 0, 0. L0, 1 has now become 1. Sorry, this is not plus. I should better use set theoretic symbol. Union, language of. Actually, this is the same as before. Yeah, 0, 1. Okay, these are all. To write it this way. L00, L10, L10, L11. This remains same as before. Okay. So now I have a partition. This machine induces a partition of sigma star in 4 parts, non-empty parts. So this is even coarser. The previous one was finer, this one is coarser, because the number of parts in the partition is smaller, even smaller, from 7 to 5 to 4. Okay. Now let us see yet a last possibility of collapsing states. It is this. If you look at this and this, if you read 1, you end up here. If you read 1, you end up here. If you read 0, you end up here. If you read 0, you end up here. Okay. So that means, again, without any problem, I can merge these two states. And that leads to the equivalent DFA with only 3 states. Now, if I look at the partition produced by this machine, this is again the same as before. Epsilon or 0 or the language of strings ending with 0, 0. L10 remains the same as before, basically the language of 0 strings ending with 10. Whereas this new state L-1 has become the language of all strings ending with only 1. Okay. So now this is a partition of sigma star in only 3 parts. So this is even coarser. Actually, you can see that you cannot make the partition coarser further. Why? For example, you cannot, this state, which is a non-accept state, cannot be equivalent to an accept state. Likewise, this and this. Now, there is a possibility that this and this can be further collapsed. And partially this is okay, because if you read 1, you will end up here. If you read 1, you end up here. But if you read 0, you will end up here. If you read 0, you end up here. So it's no further collapsing possible. And equivalently, the partition of sigma star induced by DFA cannot be made any coarser. Okay. So in fact, this is what I want to highlight in the next page. Not all partitions are realizable by a DFA. Okay. So once again, consider this same language. What is the problem if I have a two-state DFA? Of course, starting from the previous example, I cannot create a two-state DFA, because this machine itself does not offer any further collapsing possibility. Okay, but what happens if I start with some other I would say construction, not using the principle as illustrated by this example? What happens? Is it possible? So in practice, if R is a regular language, and if I consider this partition consisting of the two parts, R and sigma star minus R, this is the coarsest possible partition corresponding to R. Okay, so I will give a new name for this, corresponding to R or for R. Okay, so this is the coarsest possible partition. Now we will see that this coarsest possible partition is not achievable. For that matter, let us assume that this is achievable. So that means this corresponds to a final state. A two-state DFA accepts it, and this corresponds to a final state, and this corresponds to a non-final state. Let us give some name. Accept. This state is called reject. So I have an accept state like this, a final state T, and I have a reject state R. This is a non-final state. Okay. Now let us see that this is not possible. Why? The reason is that consider these two strings, 0, 1 and 1, 0. They are both accepted. So that means from wherever the machine starts, actually it should start from here, but that's not an important issue for the moment. If the machine reads 0, 1, it's going to accept, so it will end up at T. If it reads 1, 0 starting from the start state, it will also end up in T, because these are both in R. Now suppose a 0 comes. Okay. Then, if this 0 comes, okay, so first string becomes 0, 1, 0, the second string becomes 1, 0, 0. Now, this continues to stay in R, whereas this is not in R. Okay, which means if such a machine exists and it reads 0, it will have to stay in R, in T, because this is the only accept state, okay, by this. At the same time, because of this requirement, it should also go here. And this is not allowed for a deterministic finite automata. Therefore, the coarsest possible relation, which just consists of two parts, is not realizable. Okay. However, we have just seen that a partition of sigma star into three parts is very much possible. Okay. And this is, in a sense, we will see later, that three-part partition is the coarsest possible partition. That is, I would say, that will correspond to R and realizable by deterministic finite automata. Okay. Now, so I believe, so fine means more parts in the partition, and coarse means fewer parts in the partition. So starting from a partition which is fine enough with 7 parts, I first converted it to a partition with 5 parts, then 4 parts, then 3 parts, and then I have proved that a partition of sigma star into 2 parts is not possible. Okay. So with this example in mind, we will start doing the exact maths in order to relate machines with partitions of sigma star. But before doing that, let me recall a result taught in your discrete structures course. Partitions and equivalence relations are essentially the same thing. So let U or S be a set. Okay. Then you have seen that equivalence relations on S have a one-to-one correspondence, that is a bijective relationship, with all partitions of S. Okay, so what is this equivalence? What is this correspondence? Given an equivalence relation this, the partition is a set of all equivalence classes. And conversely, if we are given a partition, two elements of S are called equivalent if and only if they belong to the same part. Okay, so this is the correspondence. Okay, so far I have been talking about partitions of sigma star. So from this point onward, we will consider equivalence relations, in particular some equivalence relation having some interesting properties on sigma star. Recall that when we talked about the DFA minimization procedure, we introduced an equivalence relation on the set of states. But now we are talking about equivalent relations on sigma star because we are interested in partitioning sigma star by the states of a finite automaton, deterministic finite automaton. Okay. So henceforth we will consider equivalence relations, and we will not talk about partitions, but the notion of fine codes, these things can be understood if we conceive of the corresponding partition. Okay. So now in particular I will show, if I am given a machine M, I can construct a partition having some useful properties. Okay. And second, if I am given an equivalence relation with those interesting or important properties, then I can construct a machine, and these two constructions are inverses of one another. Okay. So this is what I will prove next. Okay. So from DFA to relations. So whenever I talk about DFA, I always assume there are no inaccessible states. Okay. So your input is M, which is Q sigma delta S F, such that the language of M is R, some regular language. Okay. Now I define a relation induced by M on sigma star, not on Q, such that two strings X and Y are said to be equivalent with respect to the machine M if and only if delta hat starting from S if you read X and Y, you end up in the same state. Okay. It may be a final state, a non-final state, whatever. So this is how I define this relation. It is easy to see that this is an equivalence relation. Why? For example, X is equivalent to X because delta hat SX is same as delta hat SX. Okay, if I take X equal to Y. Also, this is symmetric about the two arguments. If X is congruent to Y, I have this, but that means delta hat SY is also equal to delta hat SX. So Y is congruent to or equivalent to M, equivalent to Y with respect to the machine M. And if X is equivalent to Y, Y is equivalent to Z, delta hat SX is delta hat SY, delta hat SY is same as delta hat SZ, therefore delta hat SX is equal to delta hat SZ, therefore X is equivalent to Z. Okay, so it's clearly an equivalence relation, but actually it is more. Okay, so this is property 0. Now I have three other important properties. This is what is called a right congruence. That means that if two strings X and Y are congruent, this implies, or equivalent, this implies if I append some symbol from the alphabet sigma, they will continue to remain equivalent. Okay. Property number 2, this is true, right? If you read X and Y, you are in some state. And then if you read A, then there is a unit state you can move to, and that will be SX, delta hat SXA, delta hat SYA. So we have this, right congruence. Property number 2, we say that Okay. This relation refines R. In what sense? In this sense that if X is equivalent to M, then this condition holds. X is in R if and only if Y is in R. Okay. Now why is this true? Because these equivalence relations are characterized by states of the DFA. If it is an accept state, then both X and Y are accepted. If it is a reject state, then both X and Y are rejected. Okay, so with respect to R, so this means this. Okay, the third property, which is of importance here, this has finite index. For an equivalence relation, index is the number of equivalence classes. So in our examples, the indices were 7, then 5, then 4, then 3, and then we proved that 2 was not possible. Okay. So an equivalence relation, okay, that satisfies properties 1, 2, and 3. Okay. So an equivalence relation on sigma star satisfying the properties 1, 2, and 3 is called a Myhill-Nerode relation. Okay. So the partitioning or equivalence relation induced by a DFA M without any inaccessible states is not only an equivalence relation, it is also a Myhill-Nerode relation. Okay. Now what about the converts? Given a Myhill-Nerode relation, can I construct a DFA? Okay. So input is a Myhill-Nerode relation. Okay. The goal is to construct a DFA. Okay. So let's say this relation is given by this. Okay. Goal is to DFA which corresponds to this relation. So this correspondence I will talk about later, little later. So I build a machine M. I will build a machine M given this Myhill-Nerode relation. Okay, so it's first of all a left congruence, then it refines R, okay, for some regular language R, and this is only finite index. Okay, now since this is an equivalence relation, okay, this has equivalence classes, so my machine will be like this: Q, sigma, delta, S and F. So I need to specify this Q sigma. Sigma I don't need to specify, it's basically the input alphabet. Q, delta, S and F I need to specify given this. Okay. So the natural thing is that I will take the equivalence classes Okay, this is on sigma star. Okay, X is in sigma star. The equivalence classes are now clubbed together, okay, into single elements to form the set of states of my new machine. Sigma is the same as before. Maybe I first start with S. That is the equivalence class of the empty language. The set of final states is all equivalence classes such that X belong to R. Finally, I define delta, the delta function for my machine. So a state is an equivalence class, and you take some input symbol A from the input alphabet. It will be the equivalence class of XA. Okay. So first of all, since this is a Myhill-Nerode relation, in particular it has finite index, so Q is finite. Okay. Also, since this is a right congruence, if X and Y are equivalent, then I take any arbitrary A, XA and YA will also remain equivalent. Therefore, defining this delta in terms of this X makes sense. Okay. So this is well defined. Why? By the right congruence property. Also, it is easy to see. You just formally work it out. X is in R if and only if the equivalence class of X is in F. So this side is obvious, it follows from the definition. This side, just two lines of argument you have to mention. Okay. So this gives us a well-defined DFA and two important properties about this DFA, something like this. So I have defined delta XA to be the equivalence class of XA. Now in general I can prove that under this definition, if you take any string Y, it will be the equivalence class of X followed by Y. Okay. So proof, I leave it to you by induction on the length of Y. Fairly straightforward. Okay. Fine. So, for example, if Y is the length of Y is 0, that is, if it is epsilon, by definition, this is epsilon means nothing is read, so it will stay in X, and here X epsilon is X. Okay. And for the inductive step, you make the inductive assumption, use that assumption alongside this result. Okay. That will prove the inductive step. Fairly straightforward. So I am not going to the details. But what is important is that the language of this machine built from this is nothing but R. Okay. So why? This is also a straightforward proof, but let me formally state it. X is in the language of this machine if and only if delta hat of X I will start from the start state. Which in this case is the equivalence class of epsilon. And if I read X, I will reach one of the final states. But by this result, this is nothing but X. Okay. Take X as Y. Okay. Instead of Y, you take X. And instead of X, you take epsilon. So X is in F because of this result. And because of this result, okay, the equivalence class of X is in F if and only if X is in R. X is in R. So if X is in the language of the machine, if and only if X is in R. So I can conclude this is the language accepted by this machine is nothing but R. So this is going to be an important thing. Okay. So now that we have seen a construction, edit to end. Now we have seen a construction. Given a machine, we constructed an equivalence relation. Okay. Moreover, given an equivalence relation, we have constructed a machine. Okay. So now I ask the question, if I start with a Myhill-Nerode relation, I apply this construction, I will generate a machine. Then if I apply this construction, I will generate an equivalence relation, this. Okay. So this is one way. Another way is, if I start with a machine, I will generate an equivalence relation using this construction, a Myhill-Nerode relation to be more precise. Then I apply this construction. I generate a machine, this. Okay. Now what is the relation between this and this? And also what is the relation between this and this? So these are the two things I would just prove, or at least sketch proof. Okay. So theorem 1 maybe, another theorem. This and this relation are the same equivalence relation. It's basically the same relation. They are equal as subset of sigma star cross sigma star. Okay. So why? So let us give this machine some specific name. Q sigma S. Okay, maybe delta will come earlier. S F. Okay. And so yeah. So what are these states? Once again, let me recall. This is set of all equivalence classes X. S is epsilon, F is set of all x such that x is in R, and delta for this machine is defined as x a, the equivalence class of xa. Okay. So now suppose that x is congruent to y with respect to this. Okay. Now what does it say? By the definition of this construction, machine to equivalence relation, they are same when delta epsilon x and delta hat epsilon x, delta hat epsilon y are the same state in the machine. Okay. But then what is the same state? By this earlier result, this state is nothing but x, and this state is nothing but y. But these equivalent classes are with respect to this. Okay. So this is if and only if x is equivalent to y with respect to the original relation. So two strings x and y are related by this if and only if they are related by this. Therefore, they are the same relation. They consist of precisely the same pairs x, y. Okay. The converse of this involves a little bit more yeah. So right, so you started from M, generated the Myhill-Nerode relation with respect to the states of M. Then this is a Myhill-Nerode relation, so you use this construction to produce this machine again. Okay. Okay. So now I have to introduce something. Actually, this machine, let us call original machine Q sigma delta S F, and this machine let us call Q prime sigma M delta prime S prime F prime. Okay. In fact, if you recall this construction from Myhill-Nerode relation to a machine, so these are equivalence classes. Okay. So this consists of equivalence classes. Okay. Whereas these are individual states. So how do I show that these two machines are basically the same? These are equivalence classes, that is subsets of sigma star, whereas these are individual states. Okay. So for that matter, I introduce something called isomorphism. Okay. Let us say QM delta, let me first give the input alphabet. Delta M, start state M, set of final states for M, and let us say this is yet another DFA, Qn sigma transition delta n, Sn, Fn. Okay, we say M and N are isomorphic if there exists a bijection F from Qm to Qn such that the following three things hold. 1. The start state of M maps to the start state of N. 2. Maybe Q is a final state of M if and only if I apply this F, this will be a final state of N. And 3, the transitions are also the same. That means I start at a state Q, read A, okay. Then I apply F on it. What I will get? This will be the same as delta N. First I apply this F on Q, then I read A in N. This will be same. So this delta and F, they are interchangeable. Okay. So these are essentially the same machines with the same machine with renaming of states. And that renaming function is nothing but this F. Okay. Here also I will show that this M and this M equivalence, sub-equivalence, sub-M, they are isomorphic. They cannot be equal. So I will just prove that they are isomorphic. Okay. So M and M are isomorphic. Okay. So let us say M is something like Q sigma delta S F, and let us give it the name Q prime sigma delta prime S prime F prime. So from M you generate the equivalence relation such that X is congruent to I if and only if. So there should be some M here. Okay. If and only if delta hat S X is delta hat of Sy, and so this is basically equivalence relation, and from this we generate this where the states are equivalence classes with respect to this equivalence relation. Okay, so let us look at something one by one. I can prove all the things, this and this. Okay, maybe I will just show. Okay, let's see the first part. So okay, for that matter I have to define some F. Q prime to Q I have to define that renaming. Okay, so this is basically X, right? This is an equivalence class, okay, of some x in sigma star. This will map to delta hat s x. Okay. Yeah. So this is an equivalence class with respect to this relation. I am just mapping it to this. And I show that there are two things to show one by one. Several things I have to show. F is a bijection. Y. Maybe. These are both okay. Okay. So bijection means injective. So let's say f of this is equal to f of this. This implies, by definition, delta hat of Sx, the delta hat of Sy. Okay. But then, this says that x and y are congruent with respect to this relation. This is how that thing is defined, which implies x is equal to y. The equivalence class of x and equivalent class of y are the same. And why is this surjective? Because for every state in Q, okay, so Q does not contain any inaccessible states. So if I take any state P in this machine, original machine M, I can always find some x such that if the machine starts its operation from the start state, reads that string x, it will end up in P. Okay. So therefore, this is by surjective. So this follows from the fact that M does not contain inaccessible states. Okay, so this assumption is quite important in this context. DFA do not contain inaccessible states. Okay. Then let us see. So this is one thing, and then one by one I have to prove these three things, right? 1, 2, and 3. Maybe I will prove one. Leave the rest to you. Okay. Or whatever I can do in this page. Sorry. Made a mistake. Maybe let me first prove one. What is f of s prime? Recall that s prime is nothing but the equivalence class of epsilon with respect to this relation. Okay. And if I now apply this will map to delta hat of s. X is epsilon. But by the definition of delta hat, this is nothing but s. Okay. So f of s prime is equal to s. Okay. Maybe I just do this. Okay. 3. 2 I leave to you. 3. So f of q prime delta hat x a That's what I have to show, right? Start from yes. Okay. Okay. No. I'm making some mistake. Delta, not delta hat. Okay. Maybe. Okay, delta. And what is this? This is nothing but delta hat of S. Okay. No, I think I'm making some mistake. Just let me verify. Delta hat is x. Okay, x maps to this. So f of this will map to f of s delta hat of this state. I'm making some mistake. F of delta prime of xa. No, I should not use this at this very beginning itself. Yeah, this is delta n. So we have already proved this is nothing but f of the equivalence class of xa. Okay. And now if I use this is nothing but delta hat of s xa, right? And this is nothing but delta of delta hat of sx, sx, then a, and by definition this is nothing but delta of f of x a. Okay, and that should be it, right? F delta prime this should be delta of this. Yeah. Okay, similarly you prove 2. So these are all minor things. Okay, so to sum up, what we have seen in today's lecture is that this is the very important theorem, and this will help us prove certain thing about the minimal DFA that we will take up in the next lecture. So there is a one-to-one correspondence between these two things. One. Okay, so let R be a regular language. Between the set of all DFA that or whose language is R, and 2 the set of all Myhill-Nerode relations that refine R. Okay. In fact, you can also forget about this R. Okay. So in fact, there is also an equivalence relation or one-to-one correspondence between one set of all DFAs and set of all Myhill-Nerode relations, even without mentioning R. Okay. Anyway. Okay. So because this construction is reversible, starting from a machine, you construct a Myhill-Nerode relation and come back to the same machine, essentially the same machine. Start from a Myhill-Nerode relation, generate a machine, then once again a relation corresponding to that machine. It will be the same relation. Okay. So now because of this, I would say equivalence, maybe we will concentrate only on this first part. Second part maybe a little bit loose. Okay. So because of this, I can now talk about this R not with respect to machines, but with respect to equivalence relations, Myhill-Nerode relations to be more precise. And that is in algebraic terms. And that makes our life easier. Okay. Anyway, I think I have taken longer than 1 hour for this. So, yeah, so let us stop here. We will prove the remaining results in the next lecture. Okay, so see you.